So welcome you to today's lecture. So what we were doing so far was studying the notions of sufficiency, then minimal sufficiency, and then the completeness. Now you all may be aware that we'll have a quiz this Saturday. What is the time convenient to you? You want to have it in the morning or the evening?
Sir, I think evening will be better.
Evening better.
Sir, I will have a bit of problem in the evening actually.
You have a problem in the evening? Okay.
Sir,
Evening means whole evening or?
sir, actually that day on Saturday, I'm leaving the campus for temporarily. So I have a train on that night. So I have to set
That
up
night,
that
right?
evening.
So if I keep it at 3, would that be okay?
Yes, sir. Then no problem.
Is that 3 okay to everybody? 3 or 4?
Yes, sir.
What time is your train?
Yes.
What time is your train?
Sir, 9:30.
So then you'll be leaving around 7, right? Not before that.
Yes, sir. So
So that we can easily have it at 4, right?
okay, sir. Okay, sir.
So let us have it at 4. So it would be on Gradescope. You might have received an email from Gradescope that you need to register. So we'll have it in Gradescope, and tomorrow we'll have a tutorial. So I would encourage you to go through those homework problems, and if you have any difficulties, feel free to ask it tomorrow, or even if you can fix up an appointment and we can discuss it at any time. Okay. So there'll be.
Sir, can you please announce the syllabus of this examination?
Syllabus would be up to this homework which I gave last time, which was homework number 3, right?
Okay, sir.
Basically up to completeness, right? Up to completeness, right? So, yeah, so let us go ahead with our lecture. Any doubts anybody has from previous lectures? Okay.
Sir, one question I have in general.
Yeah.
Sir, suppose we are given that we need to prove that some statistic is not sufficient for a certain parameter.
Right.
Sir, then can we use the factorization theorem, or do we need to follow by definition only?
No, factorization theorem says a T is sufficient if and only this happens, right?
Yes, sir.
So if you have to prove using factorization theorem, it is not sufficient. How can you write down that you can never factor it like this? That would be a very complicated proof, right? So proving it would not be that easy through factorization theorem, because if you have to prove that T is not sufficient using factorization theorem, then what do you have to prove? That in no way you can factor your joint PDF as psi theta of that statistic into HX. How will you prove that? There is no way you can.
Sir, I mean, if I factor it in some way, that is not an exhaustive factorization, right? I mean, there can be other ways of factorization.
That can be only used to prove that something is sufficient, right? But if you're not able to write down something, so for example, let us say in the normal case, right? Normal, let us say consider mean as theta and variance as 1. You know that X bar is sufficient, right?
Yes, sir.
Right. Now, suppose you have to prove that median is not sufficient, right? Certainly median is not sufficient, right? For the normal theta 1 problem. Now, to show that median is not sufficient, what do you have to show if you want to use the factorization theorem? That you cannot write down your you cannot factor your joint PDF as psi of theta into median multiplied by HX. How do you prove that you cannot factorize it? You see, writing a factorization is easy, but proving that it cannot be factorized like this is a complicated job, right? Did you get it?
Yes, sir, understood. Then definition is the only way out.
Definition, no, then best thing is, you see, because you know, if you know the minimal sufficient statistic, you know minimal sufficient statistic would be a function of every sufficient statistic, right?
Yes, sir. Yes, sir.
So in this case, if you had to prove that median is not sufficient, you would say that X bar is minimal sufficient. So if median was sufficient, then X bar should be a function of median,
Exactly, sir.
right?
Yes, yes.
Is X bar a function of a median? No, because given a median, you cannot get the X bar, right? X bar is a function of a median means given median, you can find the sample mean. So given a sample median, can you
We
find the
cannot
sample
find.
mean? The answer is no. So median is not sufficient. Is that okay?
Okay, okay, sir. This is a better.
So normally when you have to prove something is not sufficient, best thing is identify a minimal sufficient statistic. And then so that your minimal sufficient statistic is not a function of the given statistic which you want to prove as non-sufficient. Does that clarify your doubt or?
Yes, sir. Thank you, sir. Thank you.
Any other doubt anybody has? Okay, so let me then just move to my slides. So I was discussing completeness last time. I gave a definition of a completeness. Then I also gave a definition of a boundedly complete statistic. Then we saw that statistic may be a family of distribution, may be boundedly complete, but may not be complete. Then we looked at various examples of complete statistics. We looked at the example of statistics which are not complete. Then we looked at the example of the exponential family of distributions, where we saw under what condition an exponential family which is of this type will provide me a complete statistic. So if your joint PDF can be factored in terms of exponential to power having k terms, eta I theta into tix, minus some term which does not depend on any observations, multiplied by hx. And if these eta i's are linearly independent, in the sense that their space eta 1, eta 2, eta k contains a k-dimensional rectangle, then this T1, T2, Tk would be minimal sufficient. That's what we saw. And then we saw that if a minimal sufficient statistic exists, then any complete sufficient statistic is also a minimal sufficient. And this was complete sufficient statistic for exponential family. Now, then we saw that the above theorem may not hold if eta is equal to eta 1, eta 2, eta k does not contain an open rectangle in Rk. And then a minimal sufficient statistic may not be complete. So this example also, we saw that if you are looking at normal theta, theta square, in this case, minimal sufficient statistic is two-dimensional. Summation xi and summation xi square, where parameter is only one-dimensional. So in this case, this minimal sufficient statistic does not turn out to be complete, and that makes sense because your parameter was only one-dimensional and you're getting sufficient statistic two-dimensional. So it looks like your minimal sufficient statistic was not very successful in summarizing the data. It still has a lot of auxiliary information or ancillary information. Why? Because you see the information about theta is contained in the mean, which is summation xi by here, as well as terms in statistic, which is called the Basus Theorem. It says that if Tx is a boundedly complete and sufficient statistic, so T need not be even complete. What I need is T is only boundedly complete and sufficient. So if it is complete sufficient, it would be certainly boundedly complete and sufficient. But I need only that T is boundedly complete and sufficient for the family of theta. Then Tx and any ancillary statistic are independent. It's a very useful result. It can be used in many situations to prove the independence of various statistics. So if a certain statistic is complete and sufficient, or boundedly complete and sufficient, and another statistic is ancillary, then the two statistics would be independent. And this supports our intuition, which was that you see, technically, if your minimal sufficient statistic has been very successful in summarizing the data, then minimal sufficient statistic should be independent of ancillary statistic. And I saw that a minimal sufficient statistic would be very successful in reducing the data if it is complete also. And that is what exactly it is saying. If your statistic is complete and sufficient, so that means it is a minimal sufficient and complete. Because complete sufficient statistic is always minimal sufficient. So what this assumption means is your statistic is minimal sufficient and complete. And this is a scenario I know where my minimal sufficient statistic is most successful in summarizing the data. So in such a situation, such a statistic would be independent of any ancillary statistic Vx. All right, so let us try to prove this. For any measurable set A, so if you're not comfortable with measurable set, you may say any set A, and T belonging to tau, define eta AT to be probability that Vx belonging to A given Tx equal to T. Because I had to show that V and T are independent. So if I can show that this eta AT does not depend on T, I'm done, because then conditional probability does not depend on the value of T, and that would prove that V and T are independent. So I need to show that eta AT is independent of T. Now, first of all, note that T is sufficient. So conditional distribution of X given T does not depend on theta. If that is the case, then probability that Vx belonging to A given Tx equal to T is independent of theta, because conditional distribution of X given T does not depend on theta. So eta AT does not depend on theta. And so eta AT is a statistic. So this is a statistic. That means its distribution does not depend on theta. I look at what is the expected value of eta AT. Expected value of eta is same as expected value of probability of Vx belonging to A given T. So it is a kind of expectation of a conditional probability. And you know that expectation and probability is a kind of expectation. Probability is an expectation of an indicator function. So it is the expected value of a conditional expectation. And you know that expected value of a conditional expectation is expectation only. So this is same as probability that Vx belongs to A. But Vx is ancillary. So its distribution does not depend on theta. So it would be some probability P of A which does not depend on theta, because V is once ancillary. So what do you get? Expected value of eta AT minus PA is 0 for every theta, where PA is some constant. This does not involve theta. Eta AT does not involve theta because T is sufficient. So it is a statistic. Eta AT minus PA is a statistic. So what do you get? You get expected value of eta AT minus PA is equal to 0 for every theta. You can consider this as some function of T. Psi T. Eta AT minus PA as psi T. So what do you get? Expected value of psi T is 0 for every theta. But T is complete because T was given to be sufficient and complete. So if expected value of psi T is 0 for every theta, that implies that psi T should be 0 with probability 1. Psi T is equal to 0 with probability 1 means eta AT is same as PA almost everywhere. That means with probability 1. What does that mean? Eta AT was probability that Vx belonging to A given Tx equal to T is same as PA. And what is a PA? PA is same as probability Vx belonging to A. So that means the conditional distribution of Vx given T does not depend on T. It only depends on unconditional probability Vx belonging to A. That means Vx and Tx are independent. Now this is a very nice result, and it turns out to be very handy to prove that two statistics are independent. Let us try to see some of the applications of this result. So let us consider this example. Let x1, x2, xn be IID normal theta sigma square, where theta belongs to R and sigma is positive. So first of all, I know that if sigma is known, then any statistic which satisfies V of x1 plus C, xn plus C is equal to V of x1, x2, xn would be ancillary. So what I have to show is so that x bar and Vx are statistically independent. And that follows just from the Basus theorem, because if V says that V of x1 plus C, xn plus C is same as V of x1, x2, xn, that would imply that V of x1 minus theta, xn minus theta, because I can take C to be minus theta, is same as V of x1, x2, xn. What does that mean? V of x1, x2, xn is same as V of x1 minus theta, xn minus theta, but x1 minus theta, x2 minus theta, and xn minus theta are IID normal 0 sigma square. That means their distribution does not depend on theta. So if I assume sigma square to be known, x1 minus theta, V turns out to be ancillary. So V is any statistic which satisfies this. Any statistic which satisfies this would be ancillary if sigma square is known. So let V be any statistic which satisfies this and does not depend on sigma square and theta. Then x bar is a complete sufficient for theta, in the normal theta sigma square if theta is known. So x bar and Vx would be independent. In particular, x bar and summation xi minus x bar whole square are statistically independent. How do you prove this? You just need to show that this statistic satisfies V of x1 plus C, xn plus C is equal to V of x1, x2, xn. Or in other words, it is ancillary. If I add everything by C, then x bar also gets added C, and C becomes cancelled. So summation xi plus C minus x bar plus C would be same as summation xi minus x bar whole square. So this is an ancillary statistic. X bar is complete sufficient. So they are independent for any fixed sigma square. And since they do not depend on, any of these do not depend on sigma square, that means x bar and summation xi minus x bar whole square are independent for any sigma square. So the way you prove it, what you do is first you fix sigma square. Then any statistic of this type is ancillary. So here assumption is that your V does not depend on theta and sigma square. But V satisfies this. Now if V satisfies this, then I conclude that such a V would be ancillary. So any such V is ancillary, and for any fixed sigma square, x bar is complete sufficient. V is ancillary. So by Basus theorem, they would be independent. Now let us consider another example. Suppose theta is fixed at theta naught. So here now I'm fixing the mean, theta naught. So variance is the parameter. And suppose V is any statistics which satisfies V of Cx1, Cx2, Cxn is same as V of x1, x2, xn. So that Tx and V of x1 minus theta, xn minus theta are statistically independent. This is certainly complete sufficient, I know. Then theta naught, when theta is fixed at theta naught, then that means theta naught is known, so summation xi minus theta naught whole square is complete sufficient. The only thing I need to show is this is ancillary, but I know that x1 minus theta naught, xn minus theta naught, V of x1 minus theta naught is xn minus theta, because V also satisfies this condition, V of Cx1, Cxn is same as V of x1 x2 xn. So V of x1 minus theta naught, xn minus theta naught would be same as V of x1 minus theta naught by sigma, xn minus theta naught by sigma, right? Because of this property that V of Cx1, Cx2, Cxn is same as V of x1 x2 xn. But what are these random variables? X1 minus theta naught by sigma, x2 minus theta naught by sigma, xn minus theta naught by sigma are IID normal 0, 1. So that means their joint distribution is the product of normal 0, 1s. So that means statistic Vx1 minus theta naught, Vxn minus theta naught is ancillary. So that means any statistics of the type Vx1 minus theta naught, Vxn minus theta naught, and summation xi minus theta naught whole square will be independent, provided V satisfies this condition, that V of Cx1, Cx2, Cxn is same as V of x1, x2, xn. As a particular case of this, the statistics x bar minus theta naught, summation xi minus x bar whole square, and summation xi minus theta naught whole square are statistically independent. How do you prove this? This is clearly of the type x1 minus theta naught, x2 minus theta naught, xn minus theta naught, because it is a sum of x1 minus theta naught, mean of x1 minus theta naught, xn minus theta naught, xn minus theta naught. And this is same as actually this. You can write down as V of x1 minus theta naught. You can take V to be V of x1, x2, x, V of t1, t2, tn to be t bar. That means mean of this square root of summation ti minus t bar whole square. Then you can see that V satisfies this condition, because if you multiply each of them by C, then T bar would become C times T bar, because each of them has been multiplied by C. Here each has been multiplied by C, so C square will come common, it goes outside. So it will become C because C is positive, so C get cancelled, and V of CT1, CT2, CTN is same as V of T1, T2, Tn. So it satisfies this. So that means V of x1 minus theta, xn minus theta naught, and summation xi minus theta naught whole square would be independent. So what is a V of x1 minus theta naught, xn minus theta naught? V of x1, t1, t2, tn was mean of all that. That means mean of x1 minus theta naught, xn minus theta naught, which is same as x bar minus theta naught. Square root of summation of ti, each of them is xi minus theta naught, minus their mean. Mean is x bar minus theta naught. So theta naught would get cancelled, and you would left with only this quantity. So this and summation xi minus theta naught whole square are independent. By the same logic, summation xi minus theta naught whole square and x bar minus theta naught square root of summation xi minus theta naught whole square would be independent, because you can write down this as V of x1 minus theta naught, xn minus theta naught, with V as t bar divided by summation ti square. In this case, you take V to be V of t1, t2, tn to be t bar and square root of summation ti square. Here also you can see V of CT1, CT2, CTN is same as C comes outside, they cancel, so the V satisfies this condition. So V of x1 minus theta naught, xn minus theta naught, and summation xi minus theta naught whole square would be independent. And that is how you get this. Because the mean of x1 minus theta naught, x2 minus theta naught, xn minus theta naught would be x bar minus theta naught whole square, square root of summation ti square. Ti here is xi minus theta naught, ti square. You can look at another example. Let x1, x2, xn and y1, y2, yn be independent random samples from normal theta 1 sigma 1 square and normal theta 2 sigma 2 square respectively, so that x bar summation xi square, y bar summation yi square and they are independent. So what I need to show is, if I can show that T is complete sufficient and V is ancillary, then they would be independent. So this is a very nice result which says that the statistic T, which implies X bar summation Xi square, Y bar summation Yi square, and Vx, which is kind of a correlation, sample correlation, would be independent. So in particular, any function of this, a function of this could be, for example, X bar. So X bar and sample correlation are independent. A function of this T is also summation Xi minus X bar whole square, which is Sx square. So Sx square and correlation are also independent. So very powerful result. What I need to prove is that this statistic is complete sufficient. That is not difficult to prove because this is a product of two normals. It can be written in exponential form. And then you can use the factorization theorem to prove that it is sufficient. You can use the result for exponential to show that it is complete. This statistic is complete. So that this, using that factorization theorem and the result for completeness for exponential families, that this is complete sufficient, straightforward. You have to just factorize E in a proper manner. Then the only thing you have to show is V is ancillary. How do you show that V is ancillary? You see, in situations where you have to show a statistic is ancillary, what you try to do is first you transform your original Xi's in such a way that their distribution does not depend on theta. That they become ancillary, or their distribution becomes independent of theta. So what I can do is I can define, let us say SI. I want to make these Xi's distribution independent of theta. So that is same as Xi minus theta 1 by sigma 1. I is equal to 1 to n. Similarly, for Yi's, I can define Ti's to be Yi minus theta 2 by sigma 2. Then what I know, because Xi's are independent, so all they would become IID. So that means S1, S2, Sn, T1, T2, Tn are IID. Normal 0, 1. So that means their joint distribution does not involve any parameter. Then what I try to do is I try to see if I can write down Vx only in terms of S1, S2, Sn and T1, T2, Tn, I'm done. Then that means the distribution of V only depends on the distribution of S1, S2, Sn and T1, T2, Tn, whose distribution in turn does not depend on any unknown parameter. So I write down these Xi's in terms of Si's. So Xi becomes sigma 1 Si plus theta 1. Similarly, Yi becomes sigma 2 Ti plus theta 2. Now I try to write down this Vx. What does Vx becomes? Summation I is equal to 1 to n Xi minus X bar. Xi is sigma 1 Si plus theta 1. X bar would be sigma 1 S bar plus theta 1. So theta 1 would get cancelled and sigma 1 would be common. So it becomes sigma 1 Si minus S bar. All right. What does Yi minus Y bar becomes? By the same logic, Yi is sigma 2 Ti plus theta 2. So Y bar would be sigma 2 T bar plus theta 2. When you look at Yi minus Y bar, theta 2 gets cancelled. You get here sigma 2 Ti minus T bar. All right. Then square root of summation Xi minus X bar whole square. Summation Xi minus X bar I have seen is same as sigma 1 Si minus S bar. So that would become sigma 1 square summation Si minus S bar square. And similarly, summation Yi minus Y bar would become square of this because that is what summation Yi minus Y bar So this would be sigma 2 square summation ti minus t bar square. So this sigma 1 square, sigma 2 square goes outside, that gets cancelled with this, and this, everything you get in terms of SIs. This is SI minus S bar, TI minus T bar by square root of summation SI minus S bar whole square into summation TI minus T bar whole square. So what do you observe? That Vx depends only on S1, S2, Sn and T1, T2, Tn. But S1, S2, Sn, T1, T2, Tn together are ID normal 0, 1. That means their distribution does not depend on any unknown parameter because that is a product of normal 0, 1s. So this is ancillary. And this anyway you have shown that x bar summation xi square, y bar summation yi square is complete sufficient by using factorization theorem and the result of completeness under exponential families. All right, so let us move. So very useful, very powerful result. Remember, if you have to prove this independence of T and V using your usual distribution theory, you have to find the joint distribution, and then the life would have been just miserable. There is no way you can do it. But see, the beauty of this result due to Basu, it says that you can prove independence just by verifying the completeness and sufficiency of one statistic and ancillarity of the other statistic. Let us look at this example. Suppose x1, x2, xn are IID uniform 0 theta, so that x1 upon xn and xn are independent, and hence so that expected value of x1 upon xn is same as expected value of x1 by xn into expected value of xn square. The result is straightforward because uniform 0 theta, you know that xn is complete sufficient. It's all right. The only thing you need to show is this is ancillary. So as I said, to show ancillary, first thing you do is you try to convert these xi's in such a way that their distribution does not depend on theta. And a suitable observation there is yi is equal to xi by theta. Because its density was of 1 upon theta if x lies between 0 to theta. So if I consider yi is equal to xi by theta, then what is the density of y is? y1, y2, yn are IID uniform 0, 1. So if I can write down this x1 upon xn in terms of yi's, that would prove that it is ancillary. And then xn and this would become independent. So note that xi becomes theta times yi. So what is x1? The minimum of x1, x2, xn. It will be minimum of theta y1, theta y2, theta yn. But my theta is positive. So if I take theta outside, because it is common to all that, the minimum doesn't change. It will be theta times minimum of y1, y2, yn, which is theta times y1. What would be xn? By the same argument, it will be theta times yn, which is theta times maximum of y1, y2, yn. So what is x1 upon xn? It is theta y1 upon theta yn, which is same as y1 upon yn. But the distribution of y1, y2, yn does not depend on any parameter because the distribution of y1, y2, yn is IID uniform 0, 1. So in the distribution of y1 upon yn, only the distribution of IID uniform 0, 1 is going to play a role. So that means this is ancillary. If this is ancillary, by Basus theorem, xn being complete sufficient would be independent of this ancillary statistic. Now then this becomes very straightforward because expected value of x1, xn can be written as expected value of x1 divided by xn into xn squared. Now this is ancillary. This is a function of complete sufficient statistic. I know that they are independent. If they are independent, their expectation product is same as expected value of x1 upon xn into expected value of xn squared. So that completes my discussion on sufficiency, minimal sufficiency, and complete sufficient statistics. If any one of you have any doubts in whatever things I did on the above topics, you may ask any of the doubts you may have today. Okay, there are no doubts. Let me just start the new module. But before that, let me save this so that I can upload it later on. This becomes today's lecture 9, I guess. Let me just save this. Let me see, this is 5, 6, 7, 8, lecture 9. No, this would be lecture 10. Let me just check just to make sure that I have saved it. Lecture 10, part 1, course 12. Now let me stop sharing. Let me come to the new topic. So what we have done so far is we have talked about the summarization of a data, which is in terms of studying sufficiency, minimal sufficiency, and complete sufficiency. So it was a complete package where we realized that sufficiency serves the purpose of summarizing the data. But then we realized that there can be infinitely many sufficient statistics. I should look for a sufficient statistic which maximally reduces the data. And that led to the concept of a minimal sufficient statistic. We saw that any one-to-one function of a minimal sufficient statistic is again minimal sufficient. So again, there are many minimal sufficient statistics. And then what is a guarantee that minimal sufficient statistic has been very successful in reducing the data? Because we saw two extreme examples. One was a Cauchy distribution where minimal sufficient statistic was n-dimensional only, the order statistic. The other extreme example was the normal case where the minimal sufficient statistic is x bar, which is one dimension. So this conveyed the message that sufficient statistic can reduce the data with a lot of variability. Sometimes it may reduce from n dimension to one dimension, sometimes it reduces from n dimension to n dimension only. So then the question arose that under what circumstances I can say that minimal sufficient statistic has been successful in reducing the data most. And that was related to the question that how much ancillary information it has. Then we realize that if it is complete, it will have no ancillary information essentially, or very little ancillary information. So that means I should look for a minimal sufficient statistic which is complete. But then we saw that any complete sufficient statistic is minimal sufficient. So if your minimal sufficient statistic is also complete, that conveys that this statistics has been very successful in summarizing the data. And in such situations where your minimal sufficient statistic is also complete, it would be independent of any ancillary statistic. So that was all a complete discussion or complete coverage of summarization of data, which is in terms of studying sufficiency, minimal sufficiency, and completeness. Now the summarization of data is being done. Now I'll be interested in estimation or making inferences about the unknown population. And that is what we'll start now. So let me just have another 10 minutes. Let me just briefly touch upon the basic concepts there. So let me share my screen. I'm going to start a new module, which is about parametric point estimation. Now, this introduction you might have already done at your bachelor's level, but let me repeat it again. So I have a random sample. So I have a random sample x1, x2, xn from a population described by a family P, which is f theta, theta belonging to theta. So I am dealing with a parametric statistical inference. So that my random sample is from a population described by the family f theta, theta belonging to theta. Functional form of f theta is known. The only thing unknown is this parameter theta. So since the functional form is known, all the uncertainty about this is contained in theta because the PDF form is known. So the only thing which is unknown is f theta. So here knowledge of unknown theta yields knowledge of the entire population because then I know the entire PDF. If I know the entire PDF, I can generate as many observations from that population. So I have the whole population at my hand if I was known because the functional form of f theta is known to us. Moreover, theta itself may represent an important characteristic of the population, such as population mean, variance, etc. And there may be a direct interest in obtaining a point estimate of theta. So if I can estimate this theta, I have a lot of information about the whole population. In fact, I have a complete information if theta was known. So I try to estimate what this theta is. Now, sometimes I may not be directly interested in theta. Rather, there may be interest in obtaining point estimate of some function of theta. So let us say tau theta for a given function of tau theta. So here the goal is based on random sample x1, x2, xn from the population. find a good point estimator of tau theta. So how can I estimate tau theta based on a random sample? So that's a basic problem I have at my hand. So I give a definition. A point estimator of tau theta is a function wx of the random sample x1, x2, xn. So an estimator of any parameter tau theta is nothing but a function of a sample observations. Now note that since x1, x2, xn are random variables, my estimator is a random variable. So note, an estimator wx is a random variable. There is also a terminology called estimate. Estimate is a realization of the estimator. Realization of the estimator after the sample has been observed. So estimator is a random variable, but after experimentation is done, you have observed the value of x1, x2, xn based on the sampling you did. And then you calculate wx, that is called an estimate. So in other words, an estimate is nothing but an observed value of an estimator. So your estimator is a random variable, whereas estimate is a fixed quantity, is a realization of a random variable. So an estimator wx is a random sample, whereas an estimate is observed value of the estimator based on the observed sample. Now note that here tau theta may take values in a certain range. And I've said my estimator is any function of a sample observation. So I have not imposed the condition that wx should lie in the range of tau theta. And I have deliberately done that just to consider the estimators in the most general form. Although it may be undesirable that wx doesn't take value in the range of tau theta, but just for the generality in the theory which we'll develop, we will not pose any such restriction. So we'll consider any estimator which is a sample of, which is a function of sample observations as the estimator of tau theta. Now what I will do now is I'll consider different methods of estimation. You have already covered some of them at your bachelor's level. So the two popular methods which you did at your bachelor's level were method of movements and method of maximum likelihood. Now both these methods are very simple to apply, and they have a lot of intuitive appeal. So what we'll do now is we'll discuss these two methods of estimation, consider various examples where you can find estimators based on these two methods of estimation. Unfortunately, I don't have much time, so I don't want to start with these new topics. So I leave over here, and I invite any questions which any one of you have. Is there anything you want to ask about the quiz? That also you may ask. Okay, anyone having any questions? So try to do those homework problems. We'll meet tomorrow to discuss your homework problems. So if now you don't have any more questions, you may leave. Others who want to stay back for clearing their doubts or asking any question, they may stay back, others may leave. Yes, any questions anybody has?
Sir, how many questions will be in the quiz?
Quiz, I may give 3 questions. It will be a long quiz, so roughly 45 minutes quiz. Each question will take roughly 15 minutes. I'll give you roughly 5 minutes to upload your question, answer responses in the grade scope. So 3
Okay, sir.
questions. Yeah, roughly 3 questions. Basically, 3 questions in all.
Okay, sir.
Is that okay?
Okay.
Yeah. I will send a mail maybe today evening or tomorrow morning in relation to this. Okay? Yes, any
Okay,
other questions? Any other questions?
Hello. Actually, sir, I have a small doubt. Like you are represent theta belongs to theta. So
Yeah.
what is the notation of? Actually, I have a problem in notations. Like theta belongs to what? Capital theta or?
Capital theta is some set, right? So for example, let me just yeah. So you see, what is happening is, what I'm assuming is, I have a family of distributions, right?
Yes.
So I have a family of distributions f theta. Theta belongs to capital theta. Now this theta could be a subset of real line, could be a subset of 0 to infinity, right? It could be a subset of 2-dimensional Euclidean space. It could be a subset of a 3-dimensional Euclidean space, and so on. So what I'm saying is, I have a random sample x1, x2, xn from, I do not know their PDF. What I know is their PDF belongs to this class, right? So it is one of the PDFs. F theta, theta belongs to capital theta. What is the exact PDF that I do not know? Since functional form of this is known, so exactly what I'm saying is I do not know what this theta is. So for example, when I say x1, x2, xn are IID normal theta 1, parameterized space I take as theta between minus infinity to infinity. So capital theta is R, whole real line, right?
Yes, sir.
If x1, x2, xn I say is IID exponential theta, in exponential theta, I know density is 1 by theta, e to power minus x by theta, if x is greater than 0.
Yes.
0 otherwise. Now, these are the equation values, so this theta has to be positive, right?
Yes, sir.
So what is the capital theta my over here? 0 to infinity.
Infinity. Yes.
Is that okay? Does that clarify a little bit to you?
Yes, sir.
Okay.
Thank you, sir.
Yeah. Any other doubt anybody has?
Sir,
Yeah.
sir, I have a doubt.
Yeah.
Insufficiency, when we talk about the normal distribution, like if xi is follow normal mu sigma square, then we say that x bar and summation xi minus x bar whole square is the sufficient statistic for mu and sigma square.
When both are unknown, right?
Yes, yes, yes.
Yeah.
But for if xi is follow normal theta comma theta square,
Right.
then also, as you have given a question in the problem set 2,
Right.
that x bar and summation xi minus x bar whole square will be sufficient for theta.
Minimal sufficient, in fact, they will also be minimal sufficient, right?
Yes, sir. So, there the parameter is same, like mean is theta and variance.
Yeah,
is
so there is only
theta
one
square.
parameter over here. So when I'm talking about, and that is what I was trying to say, when x1, x2, xn are IID normal mu sigma square, there is one situation, x1, x2, xn IID normal theta square. Now here theta can be anything from minus infinity to infinity, except 0 is not included, right? Minus 0. Here mu can be anything from minus infinity to infinity, and sigma is positive. So here there are two parameters. And here only one parameter. In both the situation, minimal sufficient statistic is x bar and summation xi minus x bar whole square. And that is what exactly I was saying, that look, what was happening in the first situation was my minimal sufficient statistic is two-dimensional, parameter is two-dimensional. So here it looks like my minimal sufficient statistic was very successful in reducing the data, because I get reduced to two-dimensional only, two-dimensional parameter, two-dimensional statistic. But in this case, what is happening? My parameter is only one-dimensional, but I'm saying my minimal sufficient statistic would be two-dimensional. So this is a situation where it looks like my minimal sufficient statistic is not very successful in reducing the data. And that suggests possibly this statistic is not complete under normal theta, theta square. And that is what exactly happens. This is minimal sufficient under 2, but it is not complete under 2. This is minimal sufficient as well as complete under 1. Right. So what is your question? This is what something I had to explain from my side. What is your specific question?
So my question is, if we're saying that x bar is sufficient for theta, why can't it be sufficient for theta square too? Or if x
No, I am not
summation
saying x bar is sufficient for theta. You see, everything is jointly sufficient. They are jointly sufficient for this family. Your sufficiency is not about parameters. Sufficiency is about whole parametric family. Here I was saying that x bar s square is sufficient for mu sigma square. Basically what it means is x bar s square is sufficient for normal mu sigma square, this situation. So I don't, when I say that x bar and summation xi minus x bar whole square is sufficient, it doesn't mean that x bar is sufficient for mu and summation xi minus x bar whole square is sufficient for sigma square. It doesn't mean that way. They are jointly sufficient. You cannot drop any one of them.
Okay, sir.
Right?
Okay, sir. Thank you, sir.
So they have to be jointly sufficient. So here also x bar and summation xi minus x bar whole square are jointly sufficient for theta. Is that okay?
Yes, sir. Thank you, sir.
Any other doubt anybody has? Okay, so if there are no further doubts, we may disperse. See you tomorrow. That's all from my side, and see you tomorrow.